Hello. This lecture will cover pages 159 through 164 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on flip-flops and related devices, Part C, the clocked SR flip-flop and toggle flip-flop. The last couple lectures we talked about three different types of flip-flops. We talked about the NAND gate latch, we talked about the NOR gate latch, we talked about the gated NAND gate latch, and the fourth flip-flop we're going to talk about is the clocked SR flip-flop on page 160 of our lecture notes. But before we get there, let's look at page 159 and talk about clocked flip-flop symbols. Very important to understand this part of the lecture. I want you to notice that when you see a block diagram that looks like this, this is an indication of a positive edge triggered. That means edge triggered. It's not level triggered. It means that this flip-flop will associate its outputs, either high, low, or no change, with a edge of a transition. And there's no bubble here, so this is what a positive edged flip-flop looks like. Over here, this is what a negative edged flip-flop looks like. So how do they actually do this? Well, if you look down here, we have our latch inside the flip-flop, and we have our steering circuits, and this used to be the enable, but it's not going to be the enable anymore. It's going to be it's going to come out of an edge detector. This edge detector, we'll talk about what that circuit is next semester. It can be as simple as just a resistor and a capacitor. However, it could be as simple as this, where if you have a pulse coming in, you get an edge on the output because the voltage across that capacitor can't change instantaneously. But that's for another course. But what I want you to see up here is how do they get an edge? How do they get this latch to change on edges? Well, the edge, the positive edge here, in this case, basically just enables these circuits. It enables the steering circuits either for set or for reset. And that's how you can take a clock input and you can make flip-flops edge triggered, either positive edge triggered or negative edge triggered. This little greater than, or this little caret here, whatever you want to call it, that means that means edge triggered. You have to look outside and see a non-bubble is a positive edge triggered and a bubble is a negative edge triggered. Setup and hold times. When you set up the inputs of a flip-flop up here, when you make this a 1 or you make this a 0, you make this a 1 or you make this a 0, you have to hold them there. You have to set them up before the clock edge, and you have to hold them there after the clock edge. That's just the way the flip-flops work. It's called setup and hold times. You have to have the input set up for a particular period of time before the edge comes, and after the edge you have to hold them there. That's how you get setup and hold times. So if you take a look down here, here's your input, one of these inputs that are getting set, getting established, if you will. In this case, I'm showing it going high. And here's the edge of the clock. That time, from the time that input goes high to the time the clock edge comes, that's called your setup time. Your hold time is, here's the edge of the clock, and here's when you take that input away. You have to keep that input active for a certain period of time after the clock edge. You have to hold it there. That's called your hold time. I want you to look in your specifications at a 7474 chip. Get your specs out and look for the 7474. And I want you to tell me if you can find what the setup and hold times are for that device. Here's your answers. The setup time is 20 nanoseconds and the hold time is 5 nanoseconds. Make sure you can do that. The fourth flip-flop we're going to talk about is called the clocked SR flip-flops. This is the first time we looked at a clocked flip-flop. Basically, here's your clock coming into the flip-flop down here. It's a positive edge triggered flip-flop. Let's see if you can see both of those. This is the block diagram, and here's the actual schematic of what goes inside here. It's comprised of a latch, some steering circuits, and an edge detector. It's a positive edge-triggered device. Here's our three inputs: set, clock, and reset. Positive edge-triggered. Here's your truth table. You don't have to memorize truth tables. Just look at the symbol. You know it's positive edge-triggered. You know things are going to happen on the positive edge. Nothing happens until the positive edge of the clock, to keep things synchronized. It's just to keep the circuit synchronized. That's called sequential logic. We're going to be getting into that more and more. You no longer just set up the inputs and some propagation time later you get an output. That's combinational logic. Now you're going to set up the inputs and you're going to clock it. And then when the clock comes, you get an output. You still have propagation delay. You can still find the propagation delay or prop time for these devices, but they're initiated by the clock. Positive edge triggered clock, and these are high active sets and high active resets. When this goes high, you're going to set the output. When this goes high, you're going to reset the output. 0, 0 is going to be no change, and a 1 and 1 is going to be not allowed, ambiguous. Look down here. On the nth clock pulse, whatever it is, when the clock pulse comes, it's the nth clock pulse. If it's 0, 0, the output's going to be no change. When Q sub n plus 1 comes, that's the next clock. Here's S sub n and R sub n are set up on the nth clock. When the clock edge comes, the next clock edge comes, you're at the output Q sub n plus 1. Well, if there's no change at 0, 0 on the clock edge, that's Q sub n. The output is whatever it was back here on when you set up the nth, the S and the R on the nth input. That's why they call it Q sub n. A 0 on S and an R on 1, it's clearly a reset because these are high active. You go 0, that's clear. A 1 on set, 0 on reset, that's a set, and the 1, 1's not allowed. Here's the circuit, here's the block diagram, here's the truth table for the clocked SR flip-flop. Pretty popular. The fifth flip-flop we're going to look at is called the toggle flip-flop or T flip-flop. And basically all you do is take an SR flip-flop, you take the Q output and you bring it around as feedback to the reset input, and you take the Q bar output and you bring it back to the input as feedback to the set input. So if you take a look, if you make the S input whatever Q bar is and you make the R input whatever Q is, this flip-flop only has one input. It's just the clock. The clock feeds in as one input, positive edge triggered, and here it is. Here's your positive edge triggered toggle flip-flop. It has two outputs. It has your Q output, and we're just going to talk about the Q output. Remember, the Q bar is just the opposite. So here's our output. Here's our input, clock, positive edge triggered, and it has a Q output. This can also come as a negative edge triggered flip-flop. I mean, you can put a bubble here and make it a negative edge triggered. But let's look at the timing diagram for the positive edge triggered flip-flop. Let's assume that the output let's assume the Q output is low. We're going to assume the Q output is low up here, and you can put your 1s and 0s on here. If Q output is low, that's going to come around and it's going to make reset low. And the Q bar output is going to be a 1, and it's going to come around and it's going to put a 1 on the set. So you're going to have a 1 on the set and a 0 on the reset. When the clock edge comes, notice what you're going to do to the output. The output is going to go high. It's going to set. And you can go through the 1s and the 0s each, and feed, and this gets set to a 1, and this is a 0, feed them around, wait to the next clock. And when you see the next clock, the Q output is going to get reset. But the proper way of looking at this is it just acts as a toggle. It goes back and forth on every clock edge. This is the way you look at this circuit. Very easy to do. Positive edge triggered. So you go to your clock, and on the positive going transitions, you draw these arrows. You're going to be drawing the arrows on the positive going transitions of the clock. And then what happens on the output, you can go through your S and your R's, but I just go down to the input and say, transition, toggle, transition, toggle, transition, toggle, transition, toggle, transition, toggle, transition, toggle. Because here's our input and here's our output. I want you to notice that the Q output toggles. This output is toggled every time there's a positive transition, if it's a positive edge triggered. And the frequency out here is 1/2 the frequency in. Take a look at the period here. The period goes from there to there on the clock, on the input. The period goes from here to here. The period gets longer. When the period gets longer, the frequency goes in half. So if you need to take a circuit and use it as a digital frequency divider, the toggle flip-flop is perfect. The toggle flip-flop can be used as a digital frequency divider. Look on page 162. For more applications, frequency divider, already talked about it. Here you have frequency in. Here you have a toggle flip-flop, positive edge triggered. Here's your output. The output goes to another input of a T flip-flop. And you could build these circuits. You know what's inside here now. The output of the second one here goes to the toggle flip-flop number 3. So frequency 1 here is frequency in divided by 2. Frequency 2 out here is frequency 1 divided by 2, which is frequency in divided by 4. Frequency 3 out here is frequency 2 divided by 2, which is equal to frequency in divided by 8. So it's powers of 2. It's powers of 2 here. If this right here was, let's make it simple. If this was, let's say 32. If this was 32 kilohertz here, 32 kilohertz here, that's going to be 16 kilohertz here. 16 kilohertz here, that's going to be 8 kilohertz here. And 8 kilohertz here, it's going to be 4 kilohertz here, which is 1/8 the 32. Take a look at that. The other thing is ripple counters, also called asynchronous counters. Ripple counters are the same thing as asynchronous counters. And you can tell when you're looking at a ripple counter, because ripple counters only have one clock input, and the output of the next one feeds the next one, the output of the next one feeds the next one. It ripples through. It's a ripple action. So I'm going to look at a 3-bit ripple counter, also called a 3-bit asynchronous counter. There's your 3 bits. Here's your QZ. I'm putting the clock in starting from the right edge, so I can make this the LSB, this is the next bit, and this is the most significant bit. It would be switched around if I'd bring the clock in on the right-hand side. So I'm going to feed the clock in so it's easier to understand here. I'm going to bring the clock in on the right side. It's a negative edge-triggered toggle flip-flop. Remember that. These are negative edge-triggered toggle flip-flops, with this being Q0, this being Q1, and this being Q2. If you take a look at page 162 or 163, I want you to complete the following timing diagram for the 3-bit ripple counter on the previous page. Well, we're going to assume the output is 0, 0, 0 for Q0, Q1, and Q2. And on the negative transition, we're looking at Q0 now. It toggles, and 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 it toggles. Now, the negative going transition here is what we have to look at for flip-flop Q1. It's low, it toggles. 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 Then the negative going transition here is what we use for flip-flop, the third flip-flop here, for output Q2. Toggles. Toggles. So if you take a look, what it's doing, if you look at Q0, Q1, and Q2, it's counting. Well, here's 0, 0, 0. So picture that back here. Picture a 0, 0, 0. That's a count of 0. After the first clock, you get a 1, 0, 0. That's a count of 1. On the next one, you get a 0, 1, 0. That's a 2. And there's a 3. And there's a 4. And there's a 5. How do I get 5? 1, 0, 1. Here's a 6. Here's a 7. It'll count from 0 to 7. That's 8 states. You get 3 bits. 2 to the 30 gives you 8 states. And then on this 8th clock here, 1, 2, 3, 4, 5, 6, 7, 8, it wraps around back to 0 again. The largest binary number counted by n cascaded T flip-flops has a decimal equivalent as 2 to the n minus 1, because 0 is the first state. So we have a 3-bit here. You can count to 7. I just showed it in this case. What if you have a 4-bit? 4-bit, you can count to 15. 5-bit, you can count to 31. And the minimum period of the clock has to be greater or equal to the number of flip-flops times the propagation time of one flip-flop, where n here is the number of flip-flops. Why is that? I mean, if you take a look at this, the period minimum the minimum period of this clock up here has to be greater than this, or this won't count. And if you put this into our frequency equation for ripple counters, the maximum frequency is 1 over this minimum period. That gives you maximum frequency. It's 1, so you just take this 1 over n times t, propagation time of a flip-flop. If this is your period, and that's the minimum, you put it in the equation down here, and it becomes the maximum frequency. This is a very important equation you have to memorize for ripple counters. The maximum frequency you can run a ripple counter at is equal to 1 over T min, which is 1 over the number of flip-flops times the propagation time of one flip-flop. So ripple counters are relatively slow counters. We're going to talk about synchronous counters coming up in a lecture or two. Synchronous counters are pretty fast because the clock goes to every single flip-flop. Ripple counters, the clock only goes to the least significant bit, and the outputs become the clock of the next one. Now, why is this the case? Well, if you look up here, it's pretty easy to understand. You cannot make this period any smaller than what it takes. This clock goes low. You have some time to make this. It takes a while through the first flip-flop for this to go low, and then for the rippling through to the next flip-flop, this is going to go low sometime later. Then this goes low sometimes later. These delays of these flip-flops here and here and here, they're stretching out into the period up here. So if this period's too small, if this clock is running too fast, you will miss state 1 the next time. You need to give it enough time when it gets back to 0 to allow this to go to 0, which will drive a propagation time later to go to 0, which will provide another propagation time later for this to go to 0. These stretch out. That's where all this is coming from down here. It's real easy to understand if you look at it, and you just use that equation. So I look on page number 164. On page 164, there's example 1. Very important you understand that and you work it out. Example 2 on page 164. Very important you read that and you're able to work that out. I gave you answers in all cases, but make sure you understand them. You're definitely going to have quiz and exam problems on something similar to this. What I was showing you is how to take a toggle flip-flop, which is nothing more than an clocked SR flip-flop with feedback from the outputs to the inputs, and make it a toggle, and then using it as a frequency divider or as a counter. And there's many applications for these counters that will be coming up. That concludes this lecture.